based on the series of factorials, inverses of factorials. But the reason he picked it that way was because he noticed that like E was kind of like a middle ground. It shows up in things like when you're calculating compound interest, because as your interest gets higher and higher, it approaches a value. It approaches a value that is usually a power of E. So this was actually just something that kept showing up, and he found a way to like nail it down. He actually didn't discover E. Well, he independently discovered it of other people, but he was the first person who used E for it. That, combined with the fact that Euler starts with E, has really made it easy to remember.
Easy. E, absolute value of Z.
Absolutely. IE is absolute value of Z.
E.
E des.
All right, Mama. Do you want to?
I started a minute ago.
Okay, that's
well,
fine.
you can edit that out.
That's actually perfect. Okay, Jared, slide. Okay, so back to here. This is just where we were before, except because this is cosine of phi plus I sine of phi, we can condense that, thanks to the wonderful thing we just learned, to absolute value of Z times e to the I phi. So yeah, that's a lot. That's really short. So next slide. So now, go back. Back. Okay. This. Oh, by the way, all these diagrams are handmade. Well, computer made. Generated.
What exactly
and
is
generated.
What exactly is this kind of saying now?
Well, okay. So basically, this is Euler's formula right here, actually, because so cosine of theta, or cosine of phi plus I sine of phi. So actually e to the I phi for any argument is going to get you what's called a root of unity, which is basically when absolute value of Z equals 1, you get a root of unity, which we will talk about. I don't want to spoil anything, but we are. But basically, they form a circle. They form a unit circle, actually, which is also kind of cool.
So essentially, Euler's formula is just a complex number graph.
Yes, it really does describe the graph of a complex number, and actually, it's one of the things that like really helps complex analysis take off. It's because it's so like fundamental and important and beautiful and great and all sorts of things.
That blows my mind just as much as the one thing. I don't know. I feel like that's like, yeah.
1 equals 1.
1 equals 1.
2 plus 2 equals 4.
Yeah, that was
A equals A.
That was, you know, on that list of most beautiful equations. Actually, Maxwell's equations beat Euler's formula, which I didn't really.
Maxwell's equations?
They describe electromagnetism. I don't really like them because I don't really think that's quite as good because like there's a bunch of equations and they're not actually very simple.
Definite sign of nerdism. Relative merits of equations.
Yeah, I think Euler's formula just looks much better than Maxwell's equations do.
It's 3 things. It's much, well, 4. Much better.
Yeah, and then after that was like a squared plus b squared equals c squared, which I actually thought was gonna win until I saw Euler's formula.
Yeah, and then it was love at first sight.
Yeah.
We should rewrite Romeo and Juliet about you and Euler's formula. I used to think that a squared plus b squared equals c squared was great, but then I saw you.
Then I saw Juliet, and I was like, oh wow.
No, Swallow, I hate everything but Euler's
Euler.
Euler.
Pens at 10 paces.
Now
Second pass. Oh, passage down.
Oh, stop. All right. Next slide.
Oh my god, man.
Okay, so everyone clear on this. So now we're going to do an instance problem. Well, actually,
What's that?
Example would have probably.
What's an instance problem?
An example. Probably would have been better to actually write example. Okay, so first, in order to express this in exponential form, we need the modulus or absolute value, and we need the argument. So first, we need to find the absolute value. So we just plug in our formula that we had before, right? So years ago.
But thank you. That was great. I apologize for your pupils'
Yeah, no problem.
dullness.
See you next time.
going.
Okay, so next thing, Jared. Then we find the argument.
Close down.
Don't actually do that. You didn't really have to do that. Just know that it looks like. Actually, when you get to trig, it'll probably be easier for you to do that.
I forgot what the argument was.
The argument's the angle.
Oh.
Yeah.
Wait, so, yeah.
Yeah, theta, or phi.
Oh.
Phi. Phi is the argument.
Oh.
Phi, are you mad?
I was already mad.
Yes.
That was actually one of my quotes from earlier.
Really?
Yeah.
Oh, that's right. I remember.
Yeah,
Yeah,
that's
you
supposed to
made
be
your
very
essay.
good. I implanted it in your
Yeah.
mind. It was Inception.
Yeah. Okay, so Eli, you got everything? All right, next thing. And finally, we convert it to exponential form by using the form. It's absolute value of z times e to the I phi. So just plug in absolute value of z and phi. You get 1 minus I equals square root of 2 times e to the I 3 tau over 8. And if you expand this, it becomes root 2. There should be parentheses around that. Oh, no, never mind. I distributed it. Okay, so it's root 2 times cosine of 3 tau over 8 plus I root 2 times sine of 3 tau over 8. Remember, you're just, I kind of skipped a step there. You're basically distributing the root 2 to the cosine of phi plus I sine of phi. And then next, I think you skipped something here. Oh no, I guess not. Okay, and then, so now these are going to help you calculate, do arithmetic with complex numbers. Not necessarily addition. Addition is way easier in rectangular form, but these operations, multiplication, exponentiation, and division, are much easier to perform in the polar form or exponential form because because you can use laws of exponents when you have a product. Like most laws of exponents apply to products. They do not apply very well to sums. Like, let me give you, so I need to write this down. So a times b quantity squared is equal to a squared times b squared. A plus b quantity squared is a squared plus 2ab plus b squared, which is more complicated. And then when you get cubing, it just gets annoying. So yeah, these are useful things to write down. Basically, we prove this by expanding each number and yeah, multiplying it. And then, so does everyone kind of understand? I suggest you rewatch the video, and we're actually kind of running out of time. But like, if you have any questions, you can tell. Okay, so cliffhanger. Sorry about cliffhanger. It's like blatant salesmanship. So z to the 5th equals 1. So z must be 1, right? You can tell it's not going to be because I put the right question. Okay, next thing.
Wait, why would z to the 5th equal? Why would we think that?
Well, because if you think about anything, you always think of like 1 to the 5th equals 1, and like whenever you're working in the real numbers, you're going to do that. Or on the bunch line. Okay, so whenever, well, I mean.
Wait, that was stupid. Never mind. I realized that.
Yeah, like if you think about it, like most of the roots of 1 that we think about are 1 or negative 1. Yeah, so because it's not an even power, you wouldn't have negative 1. But there's this number, e to the I tau over 5, and when you raise it to the 5th power, you use your laws of exponents, so you can multiply these two. You get e to the I tau, which, as we showed before, equals 1. What? But this doesn't equal 1. It feels so weird, like it's doing those rhetorical questions. Okay, next thing. Wait. So now, if you expand this is definitely not 1. So yeah, you don't need to know how I expanded this, but this is not. Just know that this is not 1. 1 has never been looked quite this ugly. I mean, you could probably make some. You could probably make 1 quite ugly, but I don't think it's really something you do. But yeah, so there's a 5th root of 1 that's not 1, and we're going to talk about that next lecture. That's called a root of unity. Next thing. That doesn't equal 1. Why is that? Come next time to find out. Next thing. And this is the end of the world.
So long with things will
As we know.
Alright, yeah, so, that's it.
Thank you for not using pi.
Oh, no problem.
Yeah, that was really nice.
Yeah, pi just makes everything confusing. And thank you, viewers.
Wait.